Welcome to today's lesson where we are going to be doing one of the required practicals for GCSE physics, and we're today going to be measuring the speed of a wave on a string. Now to do that, we've connected here a signal generator to a vibration generator which will make a wave, a transverse wave, travel along this string. It will do it very quickly, you won't see the wave actually travel, but it will travel to the pulley here and reflect backwards. So what we're going to see then is a wave that appears as if it isn't moving, but what is taking place is that the wave travels from the vibration generator to the pulley and bounces back. Now if I turn the apparatus on, using the signal generator here, we can see straight away, like I said to you, we couldn't see one wave move, but we can see that this standing wave has now been set up. So if we want to measure the speed of the wave, we need two fundamental things. We need to measure the wavelength and we need to measure the frequency of the wave. Once we know those two things, we multiply them together to work out the speed of the wave. Now if we look at this here, we've got the wave there and we've got multiple loops that have formed, and we will be using these loops to measure the wavelength, and I'm going to use a set square and some markers to help me out as well. First thing to do, I'm going to mark the position of no vibration or a node using a marker like so. Now I need to put this one in the correct place. If I place it at this position of no vibration there, you can see we've only got one loop actually of the wave, which is only equal to half a wavelength, because a whole wavelength is two loops. So if I move this marker to here now, then that means that that length now is a whole wavelength. I could at this stage then just get the set square, note the position of that on the ruler there, 40 centimetres, and this one being 63 centimetres, and work out the maths like that. However, that's not going to work because it's rather inaccurate, and the better way of measuring the wavelength will be to measure across multiple wavelengths. So if I move those, instead we can look, here is our first loop, then our second, third and fourth loop. So if we've got four loops, what we've actually got here is two complete wavelengths. Now actually looking at where we've placed the meter ruler and another meter ruler there, half meter ruler rather, we've taped that to the bench, and from here to here is 1.5 metres, so two whole waves is 1.5 metres, meaning that the one wavelength would come out at being 0.75 metres. The second measurement that we need to make is the measurement of the frequency, and that is just as simple as reading the frequency off this piece of equipment here, which is called the signal generator. The signal generator has got two main dials on it. We've got this one here, which is the range, which is currently set to 10 to 110 Hertz. So whatever frequency it's set, it is between 10 and 110. We then look at this one here, the fine adjustment, which is virtually on the 6, it's just shy of it, reading for 5.9. Now the frequency isn't 5.9 Hertz because the range is 10 to 110. So that means that the frequency on the signal generator is coming out at 59 Hertz. To find the speed of the wave, then we do the wavelength, which is 0.75 metres, multiply that by the frequency, which was 59, which gives us a wave speed of 44.25 metres per second. Now, that's how we actually go about finding the speed of the wave, but we can do an investigation to see how the speed of the wave depends on the tension that the string is under. Now you'll notice here that we've got a pulley on this end, and on the pulley dangling off the end is a set of masses. We're now going to increase the tension of the string by adding more masses onto the end. So I'll just put, for now, we're not going to obviously do an entire experiment on this video, but I'll place on there an extra 200 grams of mass, which will increase the tension quite significantly. What you'll notice, when we turn the signal generator back on, we no longer have a stable wave pattern, and we need a stable wave pattern in order to make accurate measurements. So I will now adjust the frequency on the signal generator until I get a stable wave pattern again. Now a stable wave pattern is one like this one that we've got here, where the positions of the nodes, the node displacements, aren't changing. Now that we've achieved a stable wave pattern by adjusting the frequency on the signal generator, we need to measure the new wavelength. And we do that just like we did before by using a marker at the point of no vibration there. And we could place it here, but again, that is only half a wavelength. So I'm going to move it over to here so that I've got one full wavelength. I suppose it could actually increase, but I'll go from here. Using the set square, I will put that against the sections of the ruler that have been taped onto the bench. And what I can tell you there now is that the distance between those two markers is 58 centimetres, in other words 0.58 metres. We then go back to the signal generator to see what the new frequency on the signal generator is, and I've still kept it in the range of 10 to 110, but we have changed this now to be reading 9.1, meaning that the new frequency is 91 Hertz. So the new speed of the wave comes out at being 52.78 Hertz. Now we have only done two different tensions here, but you can already see the effect that increasing the tension by adding more mass onto there shows an increase in the speed of the wave.